That's named after Robert Bunsen. And they were doing these experiments, and they would light all kinds of chemicals on fire, and they realized that every element has a unique color. And that begged a question. What question did you think that begged or inspired?
Why do the colors change?
Bam. So simple. Why does strontium produce this reddish, and why does copper produce this bluish? So this led into the whole topic of the study of light, and really led us to where we are today, where we now know it's a particle and a wave. But the next thing that happened was a resolution over the debate of whether it was a particle or wave. And at this point in time in the 1850s, the particle people were winning. So it was a big debate. And the reason why the particle people were winning, let me go turn the light on. The reason why the particle people were winning was because of a scientist you probably have never heard of, called Isaac Newton. I'm kidding. I think everybody's heard of Isaac Newton. So about 150 years before Gustav and Kirchhoff did their experiments with the colors of light, Newton proclaimed to the world that light's a particle. Now, he was such a large presence in his day in the late 1600s that certainly, as an English person, all of Great Britain, all of England would not question the great Isaac Newton. And the reason he proclaimed that light was a particle was basically he shined light through drapes, like you can see here. Now, he had really dark black drapes, and he opened up one little hole in his black drapes into his lab, and it was a bright sunny day, so the lab was completely pitch black, even though it was bright sunny day out. And he allowed one crack in his drapes to let the light through. And what did he see? He saw a beautiful ray of light jet through his lab. And, because it was probably dusty, and he just saw the dust highlight this just straight line. And so he's like, waves don't travel in straight lines, was his thought. Particles travel in these rays. So he was like, world, I figured it out, light is a particle. So all of Great Britain just fell in line, and even all of mainland Europe was like, okay, I guess he's right. Until about 1800, when Thomas Young did what's called the Young double, the double slit experiment. But we have to know something about waves before we can say, light may be a wave. And you can see this. I have all this stuff on this tray. You see this black tray here? So what we do in lab is we take these Legos and we basically build a wall midway through the tray. And we have one little slit in the wall, and we put water all over the tray. And then on one side there's water over here, there's water over here, and there's a wall in the middle. And we open up a little slit in the wall. And if I move water waves from one side, and I have these straight waves, once they hit the little slit, what will the wave look like on the other side of the wall? You can guess. Will it just travel through straight? All over.
No, it's gonna look curvy, I think.
It's gonna come through curvy. So you have these beautiful straight waves that emerge through the slit as semicircles. And that was not that like profound. It was just, okay, here's what waves do. And this was a scientist named Huygens, and it's called Huygens Principle. And the idea is when waves travel through a little slit, when plane waves travel through a little slit, they emerge as circles or semicircles. And it's not unlike if you drop a pebble in a pond, you see the waves emanate out in concentric circles. That little slit is almost like a new pebble that's being dropped right at that point. And so on the other side of the wall, the waves emerge as semicircles. So all we have to know now is, that's great. That's what waves do. If a wave passes through a slit, it emerges as a semicircle. Awesome. And so then what Thomas Young did, and everybody see this laser on the back of the wall here? You guys see that? See if I can get a brighter one. I think that's all right. So you can see that. So this is, and then let me.
I see it.
Awesome, awesome. You can actually do it. If you actually just take some hair and then shine the laser through like threads of hair, you'll see something interesting. I have these special little devices called diffraction gratings. And so what this is this piece of plastic has like thousands and thousands of little hairs or scores down it. So it's just a little bit more systematic than, just holding your hair up. And what he did is he shined. So there's, you see and then bam. Can you see? Do you see? What do you guys see?
There's 3 lights.
Oh yeah, okay, you can see it. I can't see it in mine.
Multiple dots.
Multiple spots, yeah. That's right. So the question was why?
Can you show us the Lego thing?
I can. If you give me a minute, I gotta go into the sink and get some water. You wanna wait a minute?
Yeah, sure.
Yeah, it actually is pretty cold. So let's
Sure.
give me like 3 or 4 minutes. I gotta go get some water. I'll be right back.
Okay.
Take a break.
Well, that was fun.
Yeah, we're just getting started.
We're discussing why we think the light
goes.
might diffract as a wave. So is it because of it hits something physical like the hair or the little slit, or
Homework ready.
it deflects, or is it something else?
Okay. Hey, everybody. So what I'm going to do is clean up the desk a little bit. So here's just a big, essentially baking or cookie tray of water. You can actually see the waves just kind of move. It's actually kind of beautiful just to do this. You can see the straight waves. You guys can see that?
I can see it.
Awesome. And so what we have our students do, oh, this is already kind of pre-built. Let's put a little wall there. A little wall there. And then we get a little closer. Let me just, that could work. And then we take a protractor. It doesn't have to be a protractor, but that's what we have. And then just create plane waves over here. And can you see the light reflection? Are you able to see the shape of it when it comes out?
Wow.
And I mean, I can see
No, I
these.
don't see it.
I see it.
Sometimes it depends on the light reflection. Let me try this way. You got this plane wave over here, and I can see these beautiful circles that emerge on the other side.
I see it.
Okay. And let's try it from the other angle. So this is called Huygens Principle. I can't tell if you guys can see it or not.
Sort of.
It was better the other way.
It's better the other way. Okay, well, I think that's pretty much the idea. And it is this beautiful idea in wave physics called Huygens Principle. And and so the idea was, well, if it's a wave and it goes through a small slit, when waves go through small slits, they spread out. And so when light was going through small slits, it didn't look like it spread out into these beautiful concentric circles, but something happened where there was a dot here and two dots here. So that was strong evidence that light was a wave. And they did a few more experiments, and if you have, it gets really interesting if you have two slits and not one slit. And then you have these two sets of circles that overlap, and you get this actually beautiful geometric interference pattern. And as soon as a scientist says beautiful geometric and interference, mathematicians are going to come in and say, there's got to be a formula or a pattern or relationship here. And so very quickly after the year 1800, scientists derived what's called the interference equation. And the interference equation allows scientists to calculate the wavelength of light based on how far those two dots are apart. If you guys want a little math, I think I can. Oh no, can I annotate? Yeah, I can share a whiteboard. So the interference equation is, that's the Greek letter lambda, which means wavelength, is equal to d, which is the distance between these little slits here that are so close together you can't see. Can everybody read that says 500 lines per millimeter?
What was that?
That was my phone, sorry about that.
Why is your phone making funny noises?
That was my mom who called. So I'll call her back after class. It's D, and then it's what is the equation? It's going to be hard to figure it out. So it's letter B. That's a B over C, and B and C have to do with the geometry of a right triangle. Basically, the distance between those green dots you saw on the wall. So D is easy to get. B and C are easy to get, and so it's actually very easy now for scientists to calculate the wavelength of light, or the wavelength of anything. And so all they did was shine light through these things. They measured D, B, and C, and voila, they were able to calculate. Not only is it just a profound thing to say that light is a wave. As a human being, when you look at light around you, you don't see waves, but we say it's a wave. That's a profound thing to say. But even more amazing is, okay, if it's a wave, it must have a wavelength. And scientists derived the equation to calculate wavelength. And so now we know that green laser light is about 600 and some nanometers. It actually says it right here. Red is 650 nanometers. Green is 532 nanometers. And at Quantum Camp, our students can actually, I don't tell them these actual wavelengths, and they actually go and design experiments and calculate the wavelength of green, red, and violet laser light. And so that's just a little story of the. I forgot the big concluding piece. And it turns out that color is connected, and you can kind of guess now what makes red red, what makes violet violet, and what makes green green. This is, and I may not even answer. I'll leave you guys here, and Julie, we were scheduled for.
It's because of the wavelengths. Because green, you said the wavelength was some millimeters, and so color is just how far the wavelengths of light is hitting it.
Bam! That's exactly right. And so that's exactly right. Scientists just noticed, hey, this thing that has a wavelength of 532 is green. Red light has this wavelength. And so evidently what's happening inside your eyes is when we interpret red as red, or when we interpret blue as blue, physically our eyes must be detecting something different. And Tristan said this early on, is light is a physical thing. It's not, even though it's a wave and even though it's kind of like a particle, it actually is a physical thing. And the physical things have physical properties. And the physical property of light, which impacts color, is its wavelength. And so somehow, and I'm not a biologist, our eyes are like, okay, that's 650 nanometers of energy hitting my retina. I'm going to send a signal to my brain, and then my brain tells me that's red. Somehow our eyes register, hey, that's not 650, that's 532 nanometers. That's what my retina records, sends a signal up to my brain, and my brain says, that's different than that red signal I got, so I'm going to tell this person I call Michael that's green. And so that's ultimately how so the ultimate source of what makes color is the wavelength of light.
Hey, Michael.
Yeah.
Isn't like green every color but green, and then same thing with all the other colors?
Isn't green every color but green? I would say yeah, but I'm not sure I track the meaning of the question. I think there's a deeper meaning than.
So I've been told by my brother that green is every color but green. That's the same with every other color, but it's either black or white that's every color, and then the opposite of black or white is no color at all.
Okay, so yeah, the color black is basically the absence of color. White is, Isaac Newton got this right when he said white is the combination of all the colors. And what he did is he did an ingenious experiment where he put a prism in front of that ray of light that I talked about earlier. He put a glass prism. And what happens if you put a glass prism in front of a ray of sunlight?
You get the rainbow.
You get the rainbow. And so then he took another prism where that rainbow was shining. He put the prism in front of the rainbow. Can you guess what happened? So you had two prisms, white.
White.
What?
Did it just turn into white, a beam of sunlight to white again?
Bingo. Isaac Newton separated the colors of sunlight into all the colors of the rainbow. And then he put all the colors of the rainbow back and reconstructed white light. And so that's how he was able to conclusively say, well, white light is simply a mixture of all the colors. And then the other part of your question is like, is green everything but green? If you see something that's green, maybe this is what you're referring to. So this lid is green. It's absorbing. So the light up above in this room has all the colors in it. All the colors but green are absorbed into this cap.
Yeah, so all you see is green. Since it's every color mixed together, the one color that's missing is green.
That's right.
So that's the color you see.
That's right. So that's the weird irony or paradoxical way to talk about it. Like, this thing is actually not green. It's giving off green. It's all the other colors but green. Maybe that's like the weird way to think about it. So yeah, when you see something that's reflecting light, what you're seeing is it's absorbing all the other colors. Now that's not true for things that are translucent or transparent. So if something is letting green light through, it's actually that's the same. It's absorbing all the colors but green light, and so that's letting green light through.
So that means this would be every color.
Yeah, that white string is reflecting all the colors.
And then this would be no color at all.
That, the way to think about that is that black thing it's absorbing all the colors. And
Like my headphones.
Your headphones are absorbing all the colors. And so, yeah, I'm happy to just answer questions and talk about the physics of light or the experiments I did. If you go to our, yeah, go ahead, Tristan.
Yeah, is that same for primary colors? Like if green is absorbing every color but green, would that be for yellow? Is yellow absorbing everything but yellow?
Yes, that's true for anything you see. So if you see something yellow, and now if you're getting into color mixing, that's a whole other interesting science of like why like purple, why blue and red make purple. That's actually a different domain of science, which it relies on a different set of principles. It actually has to do with biology and how our, like if both red and blue are hitting your eye, why does your eye say that's purple? I have no idea. It's a fascinating question. So if you want to do that research and get back to me, I'd love to know that. I've always wanted to know that. But that's actually something that's happening out of our. And so if you go to our, one thing you can do is, and you don't have to do it now, is if you go to quantumcamplabs.com, and I'll send this to you, Julie, afterwards.
Sure.
We have a whole course. So all this stuff here on my table, on this table, we've bundled into a little course kit with lesson plans that are almost self-guided. So a parent can like be in the room, but it's beautifully laid out such that 3 or 4 kids can, or even one student can just roll through all these experiments together. And so I skipped like 7 experiments from what is light to green is a particular wavelength. How scientists arrived at that is just such a beautiful story. I mean, I touched on some of it. First, they had to determine light's a wave. That's no small thing. Then they had to, map out the mathematics of waves, and then they designed an experiment to run lasers through diffraction gratings to back out wavelength. So there's a whole 9 labs in this course that'd be great if your group would check out. So happy to open up to questions. What else you got?
If somebody's colorblind, is it the inability of their eye to detect the different wavelengths or their brain to process them?
I do not know. So once we get into physiology and biology, I have to I'll defer you to some other teachers at Quantum Camp.
Okay.
What's a normal day like to you?
At right now, or without a pandemic going on?
Without the COVID-19?
So I teach. So I'm the founder and director of Quantum Camp, but I actually teach. I still teach 1 day a week on Thursdays, and so I teach a group of 5th and 6th graders every Thursday. 5th, 6th, 7th, and 8th graders every Thursday. And Quantum Camp has we have 50 courses. So I might not be teaching them the physics of light. We just finished a course on geochemistry. We're starting a course on evolution. We have a course on engines and entropy, which is and a lot of our courses actually walk students through the history of the development of ideas. So this course on engines and entropy walks students through this evolution from this mad dash in Europe in the 1800s and 1700s towards the development of steam engines and engines, really 1700s. And out of this came the whole science of thermodynamics and this trippy idea of entropy. Who's ever heard of the word entropy? Does anybody have any idea what? So there's this very abstract idea in thermodynamics or physics called entropy, and it's basically a measure of chaos. And I'm sure you've heard the popular way to think about entropy, and this is, you can use this, don't mention my name, but you can use this against your parents. So if your room is messy, you tell them, you tell your parents, that's just entropy at work, mom and dad. Nature tends towards messiness and chaos. And you can prove it to them by take a deck of cards that's aligned in order, like ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace, 2, 3, 4, 5, 6, 7, 8, and throw it up in the air, all 52 cards. Is it going to come back down in order?
No.
Why not? Starting order.
Because it's gonna go flying around and it's gonna fall.
But if you do that 1,000 times, shouldn't it eventually one time come back in order?
No.
I mean, it would take probably trillions and trillions of times for you to throw it up and it all come back down beautifully in order. And the reason is simply entropy. Nature likes disorder over order, and there's a good reason for that. Another way to think, a simpler way to do that is take 4 pennies, and we do this experiment in our engines and entropy class. Just take 4 pennies or coins. You guys call them pennies up there in Canada? Do you have pennies there? Okay, just making sure. Take 4 pennies and toss them. What are the chances they're all going to be heads or all tails? You have to
Very small.
very small. It's actually 1/2 times 1/2 times 1/2 times 1/2, which is what, 130, 132? 132, right? 248, 1/16. What are the chances you could get 2 heads and 2 tails?
Pretty high for me since I have 255 pennies.
Yeah, that's gonna be a to
Pretty
get them
easy.
all. Yeah, that's right. So the chances that they're mixed, like heads and tails, is much greater than if you have this beautifully ordered situation of all heads and all tails. Anyways,
I have a question for you.
yeah,
If I have 255 pennies, what percent of chance do I have that I'm not going to get 2 of one type? Like no 2 heads or 2 tails, or higher.
how many pennies do you have?
255. I can't get 2 or higher of the same type. What's the percent I can do that?
I would say that's a pretty low percentage chance. We have to
What,
run that.
like 1%?
I think infinitesimally low, like 0.0001%. Like it would never happen.
Oh, it could.
I mean, not in my lifetime. I'll put it that way. Maybe your lifetime. But you have to start now and do it every day, all day. So you better get to work after this call. But any other questions on the physics of light or other things that we do at Quantum Camp? I'm actually working on this new course called The Chemistry of Air. And
right now I'm sorting the cards in one of my decks. So so I'm gonna test it.
okay.
Once it's set up. I'm looking forward to see it actually happening.
And if you want to do something like where you can actually take data, do the penny experiment. It's really interesting, and actually make a table of data. So do it with 4 pennies. Here's the experiment we do. So take 4 pennies and roll it and toss them 50 times. So roll, 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 roll.
Wait, what was the word you told us that we can use?
Entropy. So
okay, I think I'll be using that whenever my room's messy now.
Yep, but you have to promise me you don't know me. We never had a Zoom call, okay?
Okay. You sure you want that?
I'm very sure.
Like when how about this? When my clothes aren't put away, she says, "Put your clothes away now." Well, it's entropy.
Do whatever you want, but you don't know me, okay?
Got it.
Here's an experiment you can all try that's just a fascinating window into this world of entropy and disorder. Is take 4 pennies and roll and toss them 50 times.
Are you watching the lecture?
Yeah.
But
Were you watching the lecture?
tabulate how many times you get 0 heads, how many times you get 1 head, how many times you get 2
I
heads.
was watching the lecture though. I wasn't watching the videos.
Okay, finish up. We're almost done.
3 heads. Get some background.
You mean almost done?
We're almost done the lecture. Watch the end. Okay.
So tabulate how many times you get 0 heads, 1 head, 2 heads, 3 heads, and 4 heads out of those 50 tries. Then do the same thing with like 6 pennies. Toss them 50 times. Then do 8 pennies. And then do 10 pennies. And obviously you can go up, but in class we do 4, 6, 8, and 10. It takes like an hour. It's kind of fun. You have like 15 kids just tossing pennies and recording numbers.
Okay, so should I try it now? Because I have a full deck of cards.
Okay, so Lex, just hang on. He's going to explain the experiment, and then maybe we can try it out later.
Yeah, this is awesome. You can do this all at home. And don't do it with cards. Do it with pennies.
No, I mean the full deck of cards.
Yeah, wait till I'm not near you electronically before you throw cards around your place.
No, I think I'll do it now.
Okay, Lex, let's let him finish the instructions, though.
So the data you'll get with that experiment is just so beautiful and telling of why nature prefers a disordered state over an ordered state. And we're defining ordered as all tails are all heads. That's a beautifully ordered state. And you'll see it's very rare, especially when you have 10 coins. And it actually is really fun when we do this. Like every once in a while, I'll have a group who tosses 10 pennies up in the air, and it'll come down as 10 heads. And it's actually super fun because it's so rare. But the data itself will be just really interesting. So that's just an example of another course we do. So yeah. So any other? Keep the questions coming. This is fun.
So I have one question more for me at least. So
Yeah.
for Quantum Camp, do you have any high school courses?
Yes. In fact, I'm the I do the high school chemistry.
Okay.
We're running a high school biology course right now. Again, I don't. That's not my forte. So we have another teacher doing high school biology. But now he's doing it online. So if you want to connect in, I can set you up. High school biology. So we do high school classes.
Okay. Is there anything to do with like AP Physics?
We don't. We're kind of radically not thinking about standards and tests just as a group. That's our thing. In fact, kind of like I told you, I left public schools because the state was telling me this is now, of course, we live in the real world. So what we do is for students who take our physics course, of course, some of the stuff we do is on the AP test. But we can, what students have done is before is like, they'll look at our syllabus and see what we don't cover that's on the AP test, and they'll have to study that on their own.
Okay.
And we go so much slower in a good way than like AP courses. When I was in high school, AP courses were just insane. It's like so much material. For me, the week after school ended, I didn't know anything because it was just jam and leave. So at Quantum Camp, we just do these experiments, take an hour and just roll pennies. And trust me, entropy will never leave your mind after you just spend 1 hour rolling pennies or die. So that's our approach. And the expense is we don't cover as much material in any given amount of time, of course.
I have kind of a comment / question. So you said you were working in the public school system before you began working with Quantum Camps.
Yep.
So were you part of the actual development of this camp, or did you join in after?
No, I'm the founder of Quantum Camp.
Okay, amazing. So, I mean, we're actually, this week, we're looking at how to develop our own business or product or service. So I guess my question for you is, when you were developing this service for people, what was or do you have any marketing strategies that you can pass on to us that we could maybe learn from when we're trying to reach a certain audience?
Yes, and I'm guessing you're kind of in the same way, kind of moving into the alternative education world. And so
yeah,
the first people I connected with, and there's an amazing sophisticated ecosystem of like alternative educators in the United States and probably in Canada too. And of course, it's the homeschoolers. So, and homeschoolers are a very sophisticated group. We're very well connected to each other. So I would say reach out to local homeschool groups and say, hey, we're providing these new education services, whether it's a micro school, whether it's curriculum. Homeschoolers are beautifully attracted to things that are outside the box. And now our hope at Quantum Camp is, now that we've developed all this curriculum with homeschoolers, we know it's better than what like public schools are offering. So the business mission of Quantum Camp right now is developing course kits that are easy to use by teachers who are overworked and stressed and underpaid, And most teachers are like, you want me to teach science, get out messy chemicals? You got to be kidding me with that. And 30 students. So we are making that easy and attractive for teachers to say, this is a nice kit of supplies. My kids will have fun for an hour. So that's our mission at Quantum Camp is we left the system and now we want to make the system better because the system's not going to go away. But anyways, the answer to your question is there are just these alternative groups like homeschoolers and what's the business you want to do, or what's the goal?
Well, we're actually all developing our own this week, so it's completely open-ended, but we are talking about, marketing strategies and reaching a certain audience. And obviously you have, a really elaborate website on your quantum camps. But I guess my question was more, there was a time where you had to reach a certain audience and, get people on board with your self-directed learning and, make that an appealing idea for people. So I guess my question was, what techniques could you pass on to us when we're trying to reach a certain audience or, market our ideas?
So the first thing we did is actually run summer camps. Because summer camps, you have the freedom to do whatever you want and try out new ideas. And really it was word of mouth. And that's how the idea kind of caught traction. Like if those first summer camps we ran didn't sell, then, we wouldn't have found it. So first, I would say test out whatever the thing you're trying to do is, and then and marketing. I mean, to this day, marketing is a challenge for us because there's so much out there. There's so much noise in the marketplace. It's still a challenge because you go and everybody tells me you got to have ads on Facebook and Google. I'm just not convinced, and this is just my own 2 cents. I'm not convinced that's the way to go because there's so much there. So I've always leaned towards build a great product and rely on word of mouth. And the homeschool community, homeschoolers are a very educated, very discriminating group too. So if they don't like what you have, they'll tell you and they'll pull out. So they're very discriminating. But if you're doing something good, they'll tell the world. That's been but to this day, 10 years on, I have no silver bullet. Or it's a real challenge.
Yeah, cool. Thank you.
Yeah.
How long have you been with, how long has Quantum Camp been a thing?
10 years. So we started in 2010. Now I didn't quit my day job until 2012. So I was just doing summer camps. And I had some equipment literally in the trunk of my car. And I'd rent out space at a church or a synagogue or a school for a week in the summer. I'd empty out my trunk with science equipment, had 10 or 12 students like yourselves. And so that was in 2010 and 2011. And by it took like 5 years for, there to be in any recognizable incarnation as it is today. It took like 5 years. So it's pretty slow. But I'm slower than most people, so it took me longer than most, I think. And even like the waves physics we just talked about, and the entropy, I think I mentioned most of our courses, especially like starting with like 4th and 5th and 6th and 7th and 8th grade, are literally lifted from history. The expertise of Quantum Camp is we are historians of math and science. So how was algebra created? What were they thinking when they said, hey, we need algebra? What were they thinking when they said we need calculus? Or what were they thinking when, the science of electricity was determined? We went back and we researched all those experiments, and there's these beautiful story arcs in history which led to what, we all know what defines math and science today. So the story of electricity is just a beautiful story The story of electromagnetism. We have a course on electromagnetism, which is different than the story of, just electricity. A course on, one of our greatest courses is a course on the periodic table. So Dmitry Mendeleev, he was a Siberian scientist in 1869. I'm sure you guys have all actually, behind Rowan, is that the periodic table? Rowan, look behind you. Is that the periodic table? Rowan's muted. So the periodic table was first kind of put together in 1869.
Behind Goen is the Minecraft periodic table.
Oh, that's a Minecraft periodic table. Okay. It's not the periodic table of the elements. Go ahead, Link. Do you have something?
So once, I forget which elements I combined, but I combined some random elements and made lightning.
You made lightning.
Yep, I don't know what elements I used though.
Were they gases or were they solids?
I don't know. I just combined random elements from the periodic table of elements. I don't remember.
That can happen. If you combine like oxygen and hydrogen, you can get a little spark, a little explosion. But it was.
So when I combined them, it was actually lightning, not just a spark.
Oh, you were running electricity through like graphite or something.
Actually, it's just a screen, and I tap items, and it mixes them.
Oh yeah, you did choose graph.
Yeah.
Hey, Michael.
Yeah.
Did you say when you throw up a deck of cards in order, it will never come down in order?
I will make that proclamation right now.
So it will never come down in order.
I mean, mathematically, you can't say never. There is an infinitesimal chance that when you put them all back together, they'll be in order. But I will boldly say in your lifetime that will not happen, or my lifetime. There's one other thing about the periodic table. What Mendeleev did in 1869 is he united all matter in the universe into one little piece of paper that made scientific sense. How on earth did he do that? Well, at Quantum Camp, we know there's about 200 years of data and labs and observations that scientists were making that he simply put together. It was like, guys, guess what? If we put lithium and sodium here and titanium here and argon here, there's a sensible scientific connection between all of these stuff that makes up the universe.
Well, I think we should look at the time.
Okay, I'm happy to conclude and sign off. Such a pleasure. I hope this.
So nice.
Bye.
No, wait, don't leave yet. No, this was super cool. We'll let you. We're not in a rush. If there's anything else you'd like to add,
I think that's good. I think it's a fine place to adjourn.